I'm filling in for Michele, who's unable to be here to introduce our speaker today. Raffaele Flaminio is familiar. He looked out at the audience and said he only saw two unfamiliar faces earlier on. So I guess I really don't need to do much of an introduction. Raffaele has been involved in gravitational wave detection for 15 years, 20 years, 20. So he goes back a long way. He's one of the earliest people working on Virgo. Has been with Virgo essentially the entire time, except for a couple of brief visits here to Caltech. And he'll give us an update on the status and developments and plans for Virgo. He's currently the director of LMA in Lyon, so we'll probably hear a little bit of an emphasis on the mirrors and the optics which are being coded at LMA. Raffaele?
Thank you. So, good afternoon. As Stan said, I'm at LMA since a couple of years, so I'm supposed to be the recruiting expert, which is, of course, not the case. But anyway, I will spend part of this talk talking about what we are doing at LMA for the mirrors. Before that, I will give you a brief status of where Virgo is staying and what are the motivations for doing the upgrade. I will then concentrate on the design of Advanced Virgo and the ongoing research, and then I will focus on the mirrors, and I will end with status and the planning for Advanced Virgo. So the first slide is probably useless because most of you know this. The Virgo is a gravitational wave detector based on a laser interferometer which is located in Italy near Pisa, and it is run by the collaboration of several groups, including groups from France, Italy, Holland, Poland, and Hungary now. It is operated by the EGO Consortium, which is a consortium set up by CNRS and INFN, which are the funding institution, the institution which funded the construction of the detector. So if one has to summarize the Virgo detector in one slide, basically it is very similar to the LIGO interferometer from an optical point of view. The main difference comes from the seismic isolation, which is based on a is there a laser somewhere? No. Which is based on a 10-meter tall multi-stage pendulum, itself suspended to an inverted pendulum, which provide an attenuation of the seismic noise starting from a few hertz. The other difference are the mirror, which are slightly large, about 20 kilogram mirrors. These are 35 centimeter diameter mirror with absorption at the level of 1 ppm. And then, as in the case of LIGO, the full detector is protected inside a vacuum chamber, including two 3-kilometer long tubes and several 10-meter tall vacuum chamber, one for each suspensions. So it's basically very similar to the LIGO detector. This is the sensitivity of the detector since the beginning of the commissioning 7 years ago. The red curve at the bottom is the sensitivity measure last October, which is, as you can see now, very close to the design sensitivity of Virgo. In terms of maximum distance at which Virgo can see a binary neutron star, we are around 10 megaparsec compared to 12.5 megaparsec, which is the design horizon. Virgo started the second science run last July, and the duty cycle has been quite good. Locking duty cycle is at the level of 85%. The science mode is at the level of 81%. The locking stretch are quite long. They were measured in terms of days. Longest was 6 days long. And the duty cycle was pretty good also during winter time. Usually the seismic noise is larger during winter. One have worse duty cycle. We were quite happy to see that we were able to run reliably the interferometer also during this period of the year. This is the noise budget. It shows all known noise sources compared to the measured total noise. So the pink curve is the sum of all known noise. As you can see, it's very near to the actual sensitivity. And it's also very near to the fundamental noise, thermal noise and shot noise. So if we want to improve, we need to do large hardware modification. This is how it compares with the LIGO sensitivity as measured during S5. so the two detectors have similar sensitivity at high frequency. LIGO is better in the middle range of frequencies. Virgo is better at lower frequency thanks to the seismic isolation. So as you know, these detectors are all running together. We are having joint data taking, full data sharing, and joint data analysis. There are several results that have been published now. It is clear that the present detectors are starting to test the upper limits of the predictions, but a detection, even if possible, remains unlikely, and if we want to have a more realistic rate of event, we need to improve these detectors. If we want to do start gravitational wave astronomy, we need to improve this detector, and that's the reason why we want to upgrade Virgo to a second generation kind of detector with a sensitivity 10 times better than the present sensitivity, in order to be able to increase the rate of expected event by 3 orders of magnitude. So the goal is to be online with advanced LIGO sometimes in the middle of these decades, in order to be able to do science together. I probably do not need to explain what are all the things that we can learn from this advanced detector. Maybe I should just add that the addition of advanced Virgo in the network allows to improve considerably the confidence level in the detection, and also to improve the capability of reconstructing the event and the probability to actually detect something by something which has been estimated around 40%. So it is important that we now start this upgrade, and that we come online with advanced LIGO in 5 years, let's say, from now. And from experimental point of view, it is clear that after 10 years of R&D, there are several major upgrades which are available and which should be implemented. So this is the sensitivity, the planetary sensitivity for advanced Virgo, which as usual is limited by quantum noise at high frequency, mirror thermal noise at intermediate frequency, and pendulum thermal noise at very low frequencies. But thanks to the implementation of several upgrades, all these noises are decreased by about an order of magnitude, thus moving the sensitivity in the range of the 10 to the minus 24. So how we plan to do that? So let me spend some time on the advanced Virgo design. I will not pass through all the subsystems, but I want to flash some of the main points, in particular the most important difference, let's say, respect to advanced LIGO. The first thing concerns the optical configuration. The driver for designing the optical configuration is to reduce the impact of quantum noise, to mitigate the effect of coating thermal noise, and to allow for some tunability in the sensitivity. So in practice, we will use linear recycling, which is now a mature technique, and which is compatible with our vacuum infrastructure. We will increase the cavity finesse to something around 900, and we will enlarge the spot size, the beam spot on the test mass from the present 2 centimeter to something between 5 and 6 centimeter, depending on the mirror. This will allow reducing the coating thermal noise. We will finally use DC detection in order to remove some of the difficulties, some of the technical noise which come from the use of radio frequency sidebands. One of the issues is that when running Virgo and LIGO, people have learned several lessons concerning the difficulty in running degenerate recycling cavity. It's been well experienced by LIGO and Virgo, and so in order to reduce the signal loss due to scattering in higher modes inside this degenerate cavity, and to improve the interferometer control signal, we need to break the degeneracy of this cavity. So in practice, the baseline design for advanced Virgo foresees to use a telescope inside the recycling cavity which break the degeneracy of the cavity. Of course, Virgo was not thought since the beginning to run in this condition, and so this imposes us to suspend several payloads to the same seismic isolation, which is something which is not really easy to do. So it will it will have some impact on the design of the suspension and on the commissioning of the detector, but we think we have to go through that. Another possibility which is being considered is to have this telescope which breaks the degeneracy of the cavity not between the power recycling mirror and the beam splitter, but instead between the beam splitter and the input test mass. The advantage for doing that is the vacuum chamber of Virgo allow in this condition to have longer telescopes, so to reduce the problem with astigmatism, but also it allows having a smaller beam of the beam splitter, so the beam splitter becomes easier. And finally, one can hope to play with this telescope to compensate some of the thermal effect which comes from the input mirror. So this is an alternative which is being investigated as well. I should say, to be honest, that the degenerate solution has not been completely ruled out still, even if personally I think that the difficulty we have seen with LIGO and Virgo with the degenerate cavity imposes us to change the design of this cavity and to move to non-degenerate solution. So let me now move to the laser. In this case, the goal is to reduce the shot noise, improving the high frequency sensitivity, so increasing the power injected into the interferometer by about an order of magnitude, so move to 125 watt as input power. Of course, you have drawbacks like radiation pressure noise, mirror thermal lensing, and we have mitigation of this by using heavier mirror and improved thermal compensation. The reference solution for the laser is the same as for advanced LIGO, so the use of a solid-state laser which has been developed at Laser Zentrum Hannover. It is a laser that, as you know, is composed of 3 stages, a 2 watt and pre-O master laser, then an intermediate power stage made with a power amplifier delivering 35 watts, and finally a ring oscillator injection locked delivering 120 watts and 180 watts. The advantages of this solution is the technology has been demonstrated, the noise is pretty well understood. The drawbacks is that it's a relatively complex system with many knobs and alignments to be kept under control. The laser itself is pretty inefficient. It is quite a large system. You can see a picture just of the amplifier, and it's also quite expensive. So for all these reasons, and others, I should say, in Virgo, people have been studying fiber laser since a few years. This new fiber laser, the technology of this new fiber laser is rapidly developing. They have several advantages. They are quite efficient laser. They don't need much maintenance. Basically, they are welded fibers. They are so easier to operate. The beam quality is coming out from the fiber is good. And they are quite compact, and as you can see from this picture, and they cost less. So there are several advantages. There are also some drawbacks. It's a new technology, and so as there are several aspects, the noise, the controllability of the laser, the reliability of the laser, which are not very well understood yet. But there is this R&D going on in Nice, which is giving pretty nice result. They bought one of these lasers from a company, and they were able to get 170 watt out of it. They were able to run it stably at 100 watts. In this condition, the beam quality show a very good level. The matching into the cavities was reaching 95%, and we managed to do both power stabilization and frequency stabilization. The level of stabilization we were able to reach are at the level of 3×10⁻⁹ for the power and few milliards per root hertz in terms of frequency noise, which are promising numbers. They know they can improve, they know where the limitations are coming from today, and they think this number can be improved further. So it's promising, and so the final decision for the laser hasn't been taken yet. It should be noted that probably we don't need high power laser since the beginning. Here is a picture showing the sensitivity of this detector as a function of power. What is shown here is the range that you can reach in terms of binary neutron star and binary black holes as you go up in power. So you see that decreasing the power down to 10 watts to 20 watts only loses a small factor of horizon in terms of binary neutron star and actually improve a bit the binary black hole range. So in the end, for this physics, the cost is not too much. Of course, you lose at high frequency, you lose the sensitivity to bursts coming from supernova or gamma ray bursts, but we think that the most interesting part of the physics is at low frequency, so starting at low power, it's reasonable. Now let me move to the seismic isolation. Here, of course, the main driver is to be able to isolate the mirror from the seismic noise and to control its position. The idea is to keep the seismic isolator as they are. Recently, people have made new transfer function measurement of this suspension, injecting a sinusoidal excitation at the top of the suspension, at the top stage, and measuring the displacement of the mirror using the interferometer itself. This measurement shows that the transfer function of the superattenuator is compliant with the advanced Virgo requirements. The stars are measured signals, the circle are upper limits because nothing was visible. So you can see the seismic wall at low frequency. You can see that higher frequency, all the measurements are below the requirements. So the system will basically remain as it is. From this point of view, the things that we want to change concern the control, because we have seen some limitation coming from the damping of the suspension. We have seen a sensitivity to tilt, which limit how much you can actually damp the motion of these mirrors in the range of a few tenths of milliards. This is because we don't have control of the tilt, and the inertial sensor which are used to damp the top stage actually sense the tilt and are confused by the tilt signal. At the point where they cannot be used at low frequency, where this tilt effect becomes dominant. So the idea is to develop tilt meters. There is a development going on in Virgo in order to have sensor able to measure tilt with precision of the order of 10 to the minus 8 radian per Hz at 30 millias. This is not an easy task. People are working on that since a while, but there is hope to reach that level of sensitivity and to be able to mount a tilt meter at the ground base of the inverted pendulum, and putting that in a loop with piezos which act on the bottom rim of inverted pendulum, which were already foreseen since the beginning in the design of the inverted pendulum. So this is something that we want to do for advanced Virgo. In parallel with that, there is a development of gyro laser which is going on in Pisa in order to being able to study the tilt of the ground. A prototype has been developed to that purpose, was able to reach a sensitivity of about 210 to the minus 8 radian per Hz at 10 millias, and it will be installed at the site in the forthcoming weeks, actually months, to be able to monitor the tilt of the floor of the building. The other important pieces of advanced Virgo is the suspension. There the goal is to reduce the suspension thermal noise, and so to use fused silica fiber to suspend the test masses, fused silica fiber which are monolithically bonded to the mirrors. There were relevant progress made in 2009 in this field. People is now able to produce fiber controlling precisely the geometry. They reach a very good reproducibility, and they realize a system to attach the fiber to the mirror such that if for some reason the fiber breaks, you can actually dismount the system, weld the new fiber, and remount the system. And it was tested because the fiber actually break when the first full monolithic suspension was tested last year, and in a few days we are able to recover, replacing the broken fiber with a new one. So the technology is available to the point where we stopped the data taking last Friday, and we are going to install this first version of the monolithic suspension over the next 4 months. So the idea is to have all the vapor cavity mirrors installed from now to April, and then be able to come back online sometime during the summer to restart the data taking. All the pieces we need are there. We are profiting from this stop to change the mirror with a new suprasil mirror and to increase the finesse of the cavity. We will also use the most recent coating. We are profiting from this stop also to change some of the feature of the payload. The marionettes and the reference mass which are used to control the mirrors, they have been changed in order to reduce the amount of metal near the mirror. We have seen problem with eddy currents. We have seen problem with magnetic sensitivity to external magnetic field. So now all these parts have been replaced with parts made of PEEK in order to reduce these magnetic effects. What we've shown here on the top right is the sensitivity we can achieve with this detector. The black curve is the one including all the fundamental noises. The blue curve is what we deduce from our present knowledge of the technical noises inside the interferometer. So from this curve we see that we can improve the sensitivity, and this is actually the first motivation for doing this upgrade now. So these suspension will be the ones that will be used in advanced Virgo, with an additional difficulty, as I was saying before, that as we are using non-degenerate recycling cavity, we need to suspend several of these things to one seismic attenuator. The design of that is in progress. There is some kind of waiting for the final decision on the recycling cavity geometries, but the strategy is more or less known. The idea is to transform the last stage of the super attenuator into a platform and then suspend several full payloads, 2 or 3 depending on the design, to a couple of these seismic isolators. Of course, there is some risk there. We will have to redo some commissioning of that, but it is a price that we need to pay. So let me move now into the mirrors. The main drivers there is the reduction of the thermal noise, the mitigation of the radiation pressure noise, and the reduction of the scattering coming from the mirrors. The solution is to use the state-of-the-art of the coating as it will be in 2011, when we will have to actually put the coating on these mirrors. Very likely it will be titanium doped tantalum. We will have to use larger mass to reduce the radiation pressure effect. So this will be 42 kilogram mirrors made with fused silica, 35 centimeter in diameter and 20 centimeter thick. And we will need to reduce the scattering losses. There is a quite strict requirement on the flatness of these mirrors that we hope to achieve by use corrective coating. Basically, you measure the surface of the mirror, you look where the mountains and the valley at the nanometer scale are, and you put silica at the right place in order to improve the overall flatness of the mirror. This is the reference solution that we are planning to use for advanced Virgo. So since I'm talking about the mirror, maybe I can move into what we are doing at LMA to improve these coatings. So let me have 15 minutes of advertisement about LMA, which is a service and research unit of CNRS located in Lyon, in France. It has a laboratory which has a long expertise in coatings and optical metrology. They have been working for 25 years in low losses coating. These were originally developed for gyro laser. Gyro laser need also very low losses coating, and then they were improved both in terms of quality and in terms of dimension to realize the Virgo mirrors. LMA was in charge for Virgo mirrors, and in the future LMA will realize the coating for advanced LIGO and will realize the mirror for advanced Virgo. There are other projects ongoing at LMA, one of which you may know about is the Large Survey Synoptic Telescope, which has been developed here in the United States, which actually can be at some point of some use for advanced Virgo. It is a very nice telescope that should come out more or less at the same time as advanced detectors. So At LMA we work on different subjects, among which the problem of the mirror thermal noise. There are several different kinds of thermal noise which affect the mirrors. I will not enter into the detail here. The bottom line is the coating Brownian noise is the main limitation today. This has been shown by several research, by several studies. Basically, the high index material, the tantalum pentoxide, is the lossy material which limit the overall losses of the coating. This is now well known, and it will limit the sensitivity of advanced detector, as it is shown by this red curve here on this plot. One should keep in mind when doing these studies about coating materials that you cannot use whatever material you want, because you also want to have the coating absorption as low as possible. So people are asking to have 1 ppm, half ppm, 0.3 ppm, and so this is getting more and more difficult. And this is very important because in the end it will limit the sensitivity of the detector at high frequency. It determines how much power you can actually inject into the interferometer. So you need to have not only low losses in terms of mechanical losses, but also good transparent optical material, and the choice is limited there. There are other aspects that one should keep into account. In particular, the stress in the coating can play a role on the overall performance because it can deform the surface of the mirror. It can play a role in the adherence of the coating on the substrate, and it can be a source of formation of defect inside the coating. So all these parameters have to be taken into account. The best technology we know about today in order to produce low loss coating is ion beam sputtering, at least on large surfaces as the one we want to have. We have two of these kind of machine at LMA, where basically you use an ion beam to sputter the material from a target, which then condensate on the mirror where you want to deposit this coating. So as I was saying, there are two chambers of this kind at LMA. One is of this size, the other is a 10 meter cube chamber which was built for producing the Virgo mirrors. Both these chambers are installed inside the class 1 clean room, because of course cleanliness is essential when you want to reduce losses at the level we need. We have several tools to test these coatings. The first one, it's for the measurement of the optical absorption. It's based on the thermal diffraction of a low power beam which go across the coating, which is heated by high power neodymium YAG beam. So basically by measuring the deflection of the sensing beam through the thermal gradient which is inducing the coating by the high power beam, we are able to measure losses as low as a fraction of a ppm in terms of surface absorption at the level of 0.1 ppm per centimeter for bulk absorption. This is one of the instruments we use to study the coating. The other instrument is the one which allows measuring the mechanical losses. This is based on cantilever springs, thin cantilever made of silica, which are clamped at one end. You measure the Q of the cantilever before the coating is deposited, then you measure it again once the coating is deposited. You compare the two measurements and you deduce the losses in the coating. One thing that we pay attention to is to have the geometry such that these cantilever have modes in the region of interest. So for example, we use cantilever which have first mode at 60 Hz so that we can have a measurement of the losses at the right frequency. We believe this is something important since we know that some of these losses mechanisms can depend upon the frequency. This system is able to measure Q as high as 250,000 at 60 Hz, which is sufficient to study the coating losses of both high index and low index material. So at LMA we have tried to improve this material, and we went across two different paths. One consists in developing and testing completely new material. For example, here I'm showing the results that were obtained for zirconium dioxide and niobium pentoxide. The first material is usually quite often used in optics. It has actually pretty low mechanical losses compared to tantalum pentoxide, but the absorption is too high, so it cannot be used basically because of absorption. And also the stress inside the coating is pretty high. We are at the level of a couple of gigapascal, which is a relatively high number. Niobium pentoxide has slightly larger losses because the losses that you see here are at the level of 4.6 10 to the minus 4, so they are at the same level as tantalum pentoxide, but the optical index is larger, so in practice you can deposit thinner films and get the same reflectivity. The absorption was not that bad. We measure a level about 2.25 ppm, which is a promising number. It's not as good as tantalum pentoxide, but it's something that one can hope to work on and improve. Actually, similar absorption were measured on a full mirror made with niobium pentoxide. The other path consists in trying to improve the tantalum pentoxide by doping the material with other elements. Several tests were done, and the bottom line is the titania doped tantalum remain the best solution. It allows to decrease the losses to in the range of 2 10 to the minus 4, 10 to the minus 4, and also it allows nicely to decrease also the absorption of the coating. This is a very likely situation, because as you dope the tantalum with titania, you not only increase the index of refraction, so you reduce the amount of material you need, but you also decrease the optical absorption. So everything goes in the right direction. The index of refraction increase, the optical absorption decrease, the mechanical losses decrease. It's like dreaming, and it's the best material that we were able to synthesize. By doing some optimization of the process parameters, we were able to reduce the losses in the range of 2 10 to the minus 4, and in some cases even below 2 10 to the minus 4. And the absorption, as I said, is in the range of alpha ppm. This was done both on monolayers and on full mirrors. Actually, this material was used, the first version of this material was used to coat one of the advanced LIGO Pathfinder mirrors, the so-called lusty mirror, and losses in that case were measured at the level of 0.3 ppm or less, both measured at LMA and here at Caltech. So it is the best material we have. We are doing other studies to better understand the structure of this material by using a Rutherford backscattering technique. You send helium ion beam on the coating, and from the backscatter information you can deduce the density and the composition of the film. This has been used to measure, for example, the amount of argon we have in this coating, and also to measure the density. We have seen density at the level of 7 grams per centimeter cube. This is slightly lower with respect to what you expect from pure tantalum pentoxide. We believe that this can be improved by using assistant deposition, so another ion beam which assists the deposition and help making the film more complex. This is something that we want to try in the future. So using this technique, we were able to measure the actual doping inside these different coating. I should say that the level of doping are such that actually we cannot talk about doping anymore. It's really a mixture of tantalum and titania. The number of atoms of titania is comparable to the number of atoms of tantalum, as you can see from this. And comparing different doping and different index of refraction, we end up finding the best, let's say, compromise, giving when you build the multi-layer stack the lower thermal noise. The thermal noise actually depends on several parameters. So there is a research which is ongoing at LMA to have a full repository of parameters for the different materials which can be used. And this plot shows the thermal noise, the mirror thermal noise for different coating materials. In some case, thermoelastic noise becomes important. In the case of titanium doped tantalum, the Brownian noise, it's the main limitation. This plot shows, probably you cannot see, but it shows that titanium doped tantalum is the best solution, but also that niobium pentoxide is very near in terms of thermal noise to tantalum, titanium doped tantalum. So it's a material which we think it's interesting, on which we hope we will have the time to work more. One of the things that one should keep in mind is that people want this coating to be deposited on larger and larger surface. So one should be, for example, you want the interferometer arm to be as symmetric as possible, so you want the mirrors placed in the two arms to be as symmetric as possible, and the only solution to do that is to coat them at the same time. But of course that means that you need to be able to deposit your coating in a uniform manner on a larger surface, and you need to check that when you do so when you start using this masking technique, which I use to make the coating as uniform as possible, you actually do not change the properties, the optical and mechanical properties of your coating. So this was done, this work was done, the result was positive, and based on this study we were able to produce the first twin mirrors for Virgo Plus. So two large mirrors were coated at the same time, the two input mirrors of Virgo Plus were coated at the same time, and the transmission which were measured were really very, very near one to the other. The difference in the transmission was less than a percent, which I think is the best result obtained with such large mirrors. So the conclusion is that this is an important topic for advanced detector, that titanium doped tantalum remain the best solution, and that we are able to do this coating on very large area, so doing twin mirrors and probably also in the future triple mirrors. So this is the end of the advertisement. Let me go back to advanced Virgo. There are a couple of topics that I want to touch before moving to the conclusion. One concerns the vacuum envelope. Here there is some work that we need to do because of the fact that the vacuum tube of Virgo was not baked, and so the residual pressure inside the tube is at the level of 10 to the minus 7 millibar, and that will limit the sensitivity of advanced Virgo if you don't do anything. So we need to reduce that pressure by about 2 orders of magnitude, which means we need to bake the tube. Now, in order to bake the tube, that's something we can do. We have everything to do that. But the point is that we cannot bake the chambers, the large chambers, and we cannot bake the chambers for several reasons, among which the fact that we don't want to risk the contamination of the mirror, and we don't want to bake the instrument which is around the chamber. So in the end, we need to be able to bake the tube and then isolate the tube from the rest of the vacuum chamber, which means implementing the same kind of solution which was implemented in LIGO, so installing the two cryotrap at each end of the tube. So this, from a technical point of view, it's something that people know how to do, but it takes time, and it's actually the first thing we need to do when we will shut down Virgo Plus in 2011 in order to be ready to go then to a full installation and be in time for 2015. The other point that we need to cure is the so-called culture noise reduction. We have seen in Virgo the effect of the noise coming from the machine present in the hall, air conditioning, pumps, electronics. There is some work to be done there in order to reduce the noise of the machine, and in some cases we think about actually moving out of the building some of this machine in order to reduce definitely this noise, or at least for some time. So these are things which take some time and which need to be started not too late in order to be in time with LIGO. And so And so in conclusion, there are several major modifications that we need to do. Some of these are being tested with Virgo Plus. We have already been able to increase a little bit the laser power. We have made experience with the TCS thanks to Virgo Plus, and now we are going to install this monolithic suspension and these higher finesse cavities. So this, we believe, it's something which will be very useful for advanced Virgo. The motivation for Virgo Plus is certainly to improve the sensitivity, sure, but there is also another big motivation, which is to reduce the risk for advanced Virgo. For example, Virgo Plus will be the first interferometer running with fused silica fiber, where we hope to see the effect of fused silica fibers. And so this is the timeline. We are, as I said, installing this monolithic suspension this year. We should run Virgo Plus until mid-2011, and then in around June 2011, Virgo Plus will be shut down and we'll start the installation of advanced Virgo. The goal is to being able to start the commission in 2014 and being able to reach the lock of interferometer by the end of that year. So hopefully be able to join LIGO for an advanced joint science run around 2015. So the baseline design for Virgo is now available. We also have a full cost model. The cost evaluation has been completed. The project was reviewed by an external committee, which was chaired by Barry Barish. The review lasted 6 months, between November 2008 and May 2009. At the end, the committee supported the funding of Advanced Virgo. INFN also set up a scientific committee to make a choice between the various projects which were proposed to INFN, and Advanced Virgo was ranked first by that committee. On the basis of this recommendation, the Council just approved Advanced Virgo last December. It will be funded with contribution from CNRS, INFN, the EGO Consortium, and NICEF in the Netherlands. And thanks to this approval, we were able to place the first large order, the order of a large substrate last December, which means that we have really started and that we hope to be online with advanced LIGO in 2015. Thank you.